laptop sort of up.
I would like to get started. Good morning. Thank you for coming here this morning. My job in the next 50 minutes or so is to explain how this works. This is the electric grid of the US and Canada. And we're going to talk about this grid a lot. We'll talk about the demand on the system, how that demand is met. We'll talk about the transmission system, how it works, why it's so very reliable. We'll talk about different types of generation and fuel, and maybe wrap it up with a little bit about renewables. So let's get started on this. By the way, very informal. Interrupt me if you'd like. We do have a time schedule to stick to, and I got to end right on time. So we have a lot to cover. I want to talk about this morning terms reliability criteria. We'll be talking about that. Why is the grid so reliable? We'll talk about demand characteristics and generators and fuels, as I mentioned. I want to start with terms. I realize some of you may know the difference between power and energy, but especially when you start discussing electric vehicles and batteries and things like that, I just want to briefly talk about the difference between power and energy. So here we have an electric heater. There's a meter up there that shows the power that the electric heater requires, that it demands of the system. It's a 1,000-watt heater. And right here would be the electric meter outside your house. And so if I turn the heater on, then immediately, well, that arrow didn't work. Well, it went to 1,000 watts, and then the kilowatt hour meter outside your house starts spinning. So power is an instantaneous number. It's what's required this moment. Energy is power over time. So that's why, we have kilowatt hours, and so you're charged for kilowatt hours. So for example, if this electric heater was on for 10 hours, it would use 1,000 watt hours or 10 kilowatt hours. The average cost of a kilowatt hour here in New Jersey is 18 cents. So if you ran that heater for 10 hours, you'd pay $1.80. It's simple as that. So power is instantaneous, energy is powered, integrated over time, right? All right, let's move on from there. Let's talk about in the case of electric vehicles, because I know that's going to be part of the theme of this whole convention today. Power equates to watts as horsepower. So horsepower. And then energy essentially is how many miles you can go. So you could have an electric car that has, puts out 100 kilowatts or whatever that is in horsepower. But if it has a little teeny battery, you're not going to go very far because the energy contained in the battery just isn't enough to take it very far. So again, that's why I talked about power and energy. So power, instantaneous energy over time. Now let's build an electric system. Let's start from scratch and build an electric system. Here's a little town. In this little town, they need electric power. And so let's say that Ed Smith steps up and he sells bonds and stocks and, he's an entrepreneur, gets some money. I'm going to build an electric system for this town. So what Ed does is he goes out, he builds a generating station, he builds a transmission line to a substation and then feeds that town with that substation. All right, let's just talk about this setup right here and why this is a problem, why this doesn't work very well. So first of all, let's talk about generation. So generating stations typically produce electric power at 26,000 volts. That's the typical output of a generating plant. It's about 26,000 volts. Now, in order to send that power over a long distance, we need to increase the voltage. And we increase the voltage because the higher the voltage, the lower the current in the conductors to send amount of power over the line. And the reason you want to keep the current low in the conductors, because the conductors will heat up. This is the problem Tom Edison had with his Pearl Street station system, is because it was direct current and you couldn't use transformers to change the voltage, to raise the voltage up. He had to generate the power at 120 volts and then send it through conductors under the street at 120 volts to the homes and businesses. And the problem is that there was so much in the way that there was such a loss in those conductors. By the time it got down to the customers at the end, it was maybe 100 volts. And so you had to have a power station every 10 blocks or so. But we don't have to do that now because we first of all generated a very high voltage and stepped it up even higher. So in Ed's power company here, he steps the voltage up at the substation through transformers anywhere from 138 to up to 765,000 volts. And when you step the voltage up that high, the current goes down And because the heating of the lines, the heating of the wires is inversely proportional to the square of the current. If you double the voltage, the current goes down by half, and the amount of energy you lose through the wire goes down by 4 times. So it's highly efficient. And so the transmission system, you only lose about 2% of the energy over the entire transmission system because we use such a high voltage. When you get to the other end, there's another substation to step the voltage down. And so Ed feeds this down. There's an underground cable. We don't put most transmission underground because it's too expensive and it's hard to repair. But in big downtown areas, you do have underground systems because they're very, very reliable. But again, if you have to fix something, you have to dig up the street. So it's very expensive to do that. So in neighborhoods, you don't usually, well, in your immediate neighborhood, you may have underground distribution lines. We'll talk about that, but feeding those lines is usually an overhead line, and transmission is much too expensive to bury. All right, so there's a problem with this. And the problem with this is very obvious, that if that transmission line were to get taken out of service by a tornado, there's a blackout. And that blackout could last, a week or so, how long it's going to take to put that line back in service. So right away, we have violated one of the basic criteria of the electric system that the organization I worked for, the North American Electric Reliability Council, said you can't do. You cannot have a single failure and cause a blackout. And it's called violating our first contingency criteria. So what you'll see is we developed the grid. The grid is designed so that there can be a failure of any single element, and you just don't even know it. The lights don't go out. The reason your lights go out if they do is because of a problem in the distribution system. A car hits a utility pole or something like that. It's not a grid failure. This is extremely rare. And when this happens, it upsets a lot of people and gets the government involved, and it's just ugly. Okay, so that was a problem. Ed needs to do more to fix this. So what Ed does, he builds another transmission line. So now we have 2 transmission lines from this generating plant to the town. So now if one of these lines, were to become unavailable, then there won't be an immediate blackout, but the generating station might fail. So we've still violated our single criteria. We have a single failure, the generating plant, and so there's another blackout. Transmission's in better shape, but the generation is gone. So we have a blackout, and that could last weeks. So Ed's not done. So what Ed needs to do now is build another generating station. So Ed builds another generating station at the other end of the service territory with a transmission line. Better, but not really outstanding. So first of all, if this line were to become unavailable suddenly, you would have a partial blackout. Why would you have a partial blackout? The reason you have a partial blackout is because now you put the entire demand of the system on this one plant, and you cannot increase the output of a generator from here to here instantaneously. It won't do that. If you have a steam generating plant, then it could take an hour to bring the output from here to here, because you've got to put more fuel in the boiler, you've got to heat the boiler, you need to make more steam and everything else. So you'll have a blackout, it may not last as long. So this is still not good. We're not there yet. So what Ed needs to do now is complete the network, complete the transmission network. And literally he builds a loop around the city, which is very common today to have a loop around a major city, a transmission loop. So now we have this generating plant and that generating plant connected with 2 different paths, so that if this transmission line goes out, no one knows. Because there's another path for the power to go out of this plant up and around the transmission system and serve the city. So you still have 2 generators connected to the network. One of the lines is out of service, but so in this case, it's much less vulnerable to failures of the transmission network. And we use the word network because every major substation is connected by at least 2 transmission lines. And so if you go around town and you look at we're talking about the lines up on the big steel towers. And if you look at a substation where the lines come down, there's a transformer and they may feed some neighborhoods or something, you'll always see 2 lines coming in from different directions. So that if one line were to become unavailable, that substation would still be served by the other line. We stop there. Any questions about this? Is very key to how the grid works. So we're talking about, yes, sir.
So maybe not something you specifically spoke to, but nomenclature that I've heard that perhaps you could explain. It's like N1 or N2 reliability to reflect how many.
Right, excellent. So this is called N-1. In other words, you have the number of elements in the system. It needs to be able to survive without a blackout with N-1. So this is the -1, right? That's, thank you for asking that question. Now, there is an N-2 criteria that says, well, if you really want to build it robust, then you should be able to withstand the loss of at least 2 elements. I don't know that this system would be able to do that, but if we connect this to other utilities, it might be, then you might see where that is going to work. But N-1 is the criteria. So the loss, when I say loss, the failure of a generator transmission line would not cause a blackout.
So just to follow on,
Please.
so if you have your own generating capacity, like a cogen facility, would that be, and you're simultaneously grid connection as well?
Right.
Is that N2 negative?
Not necessarily. N-2, I'm trying to think of where that might come in. It might come in where you've lost one item and now you're sitting there a bit more vulnerable. And in that case, you may decide in that for your system that you really want to go to an N-2. It depends on the customers you're serving. So my guess is for a downtown area like Manhattan, my guess is that Con Edison probably operates their system through N-2. In other words, they could have the failure of this element and this element and no problems in Manhattan.
So it's Manhattan, having worked at Con Ed.
Ah, very good.
-3.
N-3, good. Oh, wonderful. I did not pay this gentleman to come here. What did you do at Con Edison?
I was the section manager for energy efficiency.
Okay, great. Oh, good. So I got someone to keep me honest. Excellent question. Very, very good. So it depends on the area that you're serving and how critical it is. Yes, question.
So a brownout, would I be correct then to assume that a brownout is what happens when you've lost like one but still have a little bit of, or is that while one substation is ramping up, or what exactly does a brownout?
That's the question. What is a brownout? Okay, so there's a brownout and there's a blackout. Neither are good. The blackout's worse. I mean, there's no service. A brownout is typically what happens when you don't have sufficient generating capacity to serve all the demand. It's a really hot day. You've got some generating units that are out and you can't quite meet the demand on the system. Almost, but not quite. So you don't want to shed load. In other words, you don't want to black out customers and bring that balance back between generation supply and the demand. What you do is you lower the voltage on the network, usually on the distribution network. That's why it's called a brownout. You probably can't tell that it's happening, but it's the voltage is a little lower. That brings the demand down enough to ride through that peak period. So that's the difference between brownouts like that.
Okay.
Yeah, excellent questions. All right, let's continue building our grid. All right, now this is still an isolated system. It's isolated. It's not connected to anything else. We've added a distribution system at the top to serve some customers. Now, distribution, my arm is not long enough, but anyway, so off of this power substation here in the middle and off of that, and we've built a lower voltage called subtransmission. It's just a lower voltage. It's still a network. It loops around and lower voltage, and it connects to a substation that drops the voltage from, let's say, 69 or 138,000 volts down to 12,000 to 34,000 volts. And then that is what feeds the neighborhoods. All right. So that's what you'll see on the wooden power poles is 12 to 34,000 volts. The distribution network, well, the distribution system is not a network. Yes, question?
Can you re-say that?
Pardon? Yes, I will re-say that. To serve the distribution, to serve residential customers and small commercial customers, we serve them at a lower voltage.
Okay.
And so in this case, we've built a subtransmission network that ties between these two power substations at a lower voltage. It's cheaper. I mean, you don't need that heavy, you don't need super high voltage to do that. So anywhere from 138 to 69 to 138,000 volts is considered subtransmission. If you go up Route 1 and you look at the tall wooden poles on either side at the very top, those lines at the very top are 69,000 volts. And so that's serving the Princeton, Trenton, West Windsor area, going up all the way up to New Brunswick. So it's lower voltage. It's not the high long distance transmission. It's lower voltage. And then from there, it connects to what we call a distribution substation. It steps the voltage down to 12,000 volts. And then it goes under, usually often underground or overhead. And then if you have an underground network in your subdivision, you'll have a big green box in your front yard. And it comes in at 12,000 volts and gets converted to 120, 240 that serves your home. So that's the whole chain from generation through transmission up to distribution and then to your home. So that's that whole chain there. Okay. Got it. All right. So we're still isolated. We're not connected to the grid yet. We are serving distribution customers now. And now we're going to add a wind turbine farm down here. Wind generating plant will generate a lower voltage. By the way, let me back up a second. Let me get back to Manhattan. Large cities have an underground distribution network. It's not radial, it's a network. Highly reliable. Highly reliable. And so in that case, in your house, if someone knocks down a power pole, then all the lights go out. It's like a Christmas tree. Okay? They all go out. And it'll take a while to bring that back. You can't have that happen in downtown New York or Philadelphia or Seattle. And so the underground distribution network is indeed a network, and it's all interconnected. And if you have a major problem, you have to dig a hole sometimes and cut things apart. I mean, it can be very difficult to repair. Highly reliable, though, very, very reliable. So in this case, now we've added a gas turbine generating plant up here, which is a quick start plant. That helps. It uses, and we'll talk about gas turbine generators. They're very, very useful. They don't run a lot, but they're very useful. And then here's a wind turbine generating plant that's tied into the substation here at some lower voltage. Somewhere here, there's a control center in some nondescript building, someplace that's monitoring all this. Also important, we don't switch transmission. This is not like the telephone system. Well, the telephone system really isn't like the telephone system anymore anyway. Well, it's more like the internet. So this is always connected, continuously connected. And so the system operators don't route power. Flows over all the paths, follows the paths of least resistance from the sources to the loads. That becomes very interesting when you start interconnecting with other systems. So now we're going to tie it to the grid. You can see in the upper right corner and lower right corner, we now have tie lines. We're now going to tie this system in with neighboring systems. And this is great because now we can share reserves. So for example, when this was an isolated system, let me back up just a second here. When this is an isolated system, Ed's company here needs to keep twice as much generation spinning and ready to serve load as there is demand. Twice as much, because if one fails, the other generating plant has to quickly pick up that demand or else you cause a blackout. So Ed needs to keep at least half of his total capacity as what's called spinning reserve. But as soon as Ed connects to other utilities in the grid, and you have something like this, now utility A, this could be Ed, and there's B, and there's C. These utilities can get together and come up with a reserve sharing agreement, where instead of having to maintain twice the generating capacity online, they can share the spinning reserve. And so maybe Ed keeps 20% extra, and maybe utility B keeps 30%, and utility C keeps 20, 50%, depending on the size. Because now you can use the diversity of the grid to help you out, because the chance that you're going to have several generating units fail at the same time is very remote. It's quite remote. So by connecting yourself to other systems, you can take advantage of the diversity in the system and share in the spinning reserve. You can also begin economic trades with other systems. So there are times, for example, when Con Edison could buy power from maybe, the PJM interconnection at a cheaper rate. Because, and we'll talk about PJM, but because Con Ed is tied to PSE&G and Orange and Rockland and other systems, they could buy energy from time to time. They could even engage in long-term contracts. They can be they can play in the power market. And so being connected is very important. Yes.
Aren't you like buy energy, or what's the price for the amount, for an amount of energy?
I'll give you a simple example, but I could spend another hour on energy markets, but it's a good question. Let me give a real simple example of how it's done in some parts of the country. All right. Utility A, Ed is generating from coal. And he has additional generating capacity he's not using, and he can generate from coal at $20 a megawatt hour, right? Now, Sally's electric company over here is generating, is about to have to turn on a gas turbine to supply the peak demand. And that gas turbine is going to cost $40 a megawatt hour to run. So if Sally can avoid starting that gas turbine, her avoided cost for that hour would be $40. Meanwhile, Ed could sell at $20. And so they'll come together and they'll agree to sell at $30. And so Ed will sell Sally's company 100 megawatts, let's say at $30. Ed makes $10 a megawatt hour. Sally saves $10 a megawatt hour. We call that A plus B over 2. And that's like a broker system. When you get into energy markets, it gets much more complicated than that. And I wish I could go into that today, but I can't. And there are large market areas in the Northeast, in California, and in the Midwest, and not so much in the Southeast and other parts of the countries. But you've got to be connected in a grid in order to take advantage of economic transfers and the extra reliability that comes from the diversity of sharing reserves. I just gave you an awful lot. Is everyone with me? Because we're going to blow this up some more in a little while. Figuratively, not literally. Okay, so now you see how the grid works, and this is what we have today. This is the really extra high voltage. This does not show. There's a lot of 230,000 volt lines. I don't know if the next one shows that or not, but this is a pretty high view of the grids. And so there are essentially 3 interconnections in the United States and Canada. You know, why 3? I mean, well, actually 4, because I didn't show Hydro-Quebec is up there as well. When you have generating units that are connected together, they're actually connected electromagnetically together. Generating units in an alternating current system that we have in the US and Canada that's providing 60 cycle per second current, then you get 3,600 RPM. And they're synchronized. They have to be synchronized. And so when you bring a generating unit online, you add the steam and it comes up to speed, you then have to synchronize it to the network. And so the generators in Miami and the generators in Manitoba and over in Oklahoma and up in Maine are essentially spinning at the same speed. Okay. And if you were to, at a generating unit, if you were to turn the steam valve off and not disconnect the generator, it would continue to run as a motor. It would run as a motor. And so again, the generators are all electromagnetically connected to each other. It's one giant machine with a lot of inertia. Now, if we look at the grid over here, most of the load, most of the customers, and most of the generation in this part of the country is over here in this area, and also the Midwest. You go to the western part of the United States, most of the customers and generation is over here in the western part of the western US. And in order to reliably connect this network of generators with this network, you have to build a lot of transmission across the Rocky Mountains. Because if you only had 1 or 2 transmission lines across here, they would lose synchronization. It just won't work. It just won't work. You have this huge, massive rotating metal over here, and there isn't enough wires in the air to keep them connected. And so you end up with stability problems. And so that's why there are separate grids. There are some small, what are called AC/DC, AC converter stations, where they can trade some energy, they can sell, but not much, not much. So Eastern and Western interconnections are not synchronized with each other, and it would cost too much to keep them synchronized. Texas is independent because it's Texas. Texas, if you interconnect across a state boundary, you come under the jurisdiction of the Commerce Committee, federal commerce. You're engaging in interstate commerce. And so you come under the rules and regulations of the federal government. Texas wanted no part of that back in the 20s, last century 20s. And so they've remained an isolated grid, a big one, but they've remained in an isolated grid. They are big. And 2 years ago, we won't go into that. I wish I could. It was very interesting what happened here in February a couple of years ago, because they also decided they just didn't want to have any kind of government regulation at all. They left the whole electric system to the marketplace. And you saw what happened back in February of 2021, I guess it was a mess. Another topic, another day. Hydro-Quebec, most of the generation in Hydro-Quebec is up around James Bay. Most of their demand is 700 miles to the south in Montreal and in Quebec City. And they really cannot keep that network synchronized with the Eastern interconnection without a lot of transmission. It isn't worth the cost. So Hydro-Quebec is an isolated network, also big, but isolated. So those are the interconnections we have in the US and Canada. And the organization I worked for wrote the rules for operating this. Now, I'm retired. It's been a while since I worked there, but it was an exciting job. It was wonderful. I really loved it.
You have direct current on there too.
Yeah, there are. Well, that's, yeah.
comment about
I
that?
just happened to mention that there's a direct current line here and here. That's an interesting point. So one thing you can do is, so between the Dalles generating plant up in the Pacific Northwest in Los Angeles, and then over here in, I don't know if that's not corners, not sure which generating station that is. There's another DC line here. So how does DC work? And that's what Edison did. He used direct current. That's that didn't work, but it does at very high voltages. And so what you can do is, if you want to send power over a really long distance, nonstop, like 700 miles, nonstop, then you have generation here, and you send the generation through a giant diode and a filter. Okay, and now you first step it up to 500,000 volts. You run it through a solid state or a mercury diode, whatever they're using, rectifier, and now you've got direct current, and you can send that from here to wherever very efficiently, very, very efficiently. At the other end, you have an inverter. The terminal equipment at either end is very expensive, so you don't do that much. It's not something we often do. But if you really want long haul power, electric power, DC transmission is the way to go. And so if you look at the transmission line between Oregon and down into LA, it's a tower with just 2 wires on it, not 3, because in AC current, we generate 3-phase power. There's 2 lines on it, 500,000 volts positive to ground and 500,000 volts negative to ground. So 1,000,000 volts between the two, highly efficient. So I'm glad you noticed that. So yes, there is some DC, and DC does go a long way. It's all to do with the voltage. Yeah.
What size wire?
Oh,
For that.
about that. I don't know the exact diameter. That's a good thing to look up. It's aluminum conductor steel reinforced. So it's got a steel wire core and it's got aluminum on the outside. And I can't tell you how big around it is. It's bigger than you think. Because you look at it and what does it look like? But it's big stuff.
Well,
Heavy.
that would actually be smaller than I think.
It might be. It could be. I mean, this is the grid. When you go down to 69,000 volts, this is what it really looks like. So there's a lot there. And so we call that the bulk electric system. I don't show the generators and substations here, but the generator, substations, and transmission network all make up what we call the bulk electric system. So let's look at the demand characteristics. This is very important when you start talking about electric cars and when you're going to recharge them, and you'll probably see a pattern right away. So up in the upper corner, there is a map of the PJM network that we're a part of. PJM, Pennsylvania, New Jersey, Maryland. It's a large power market reserve sharing area. It's been around for decades. And then after deregulation, maybe 15, 20 years ago, they actually merged with a lot of other systems. And now PJM goes from the mid-Atlantic states all the way to Chicago. So it used to be Commonwealth Edison, I think is owned by Exelon, is now a part of PJM. Huge area, huge area. There's a control center for PJM. It's in Valley Forge. No, it's not that far from here. In a very nondescript building. It's mostly underground. So you can't get into it, which is a good thing. Anyway, so these are the shape, these are what I call demand curves. And so if you look at the summer demand for PJM, up to 100, well, that was probably last year, I guess. They had a peak demand of about 115,000 megawatts on that particular day. And so you can see that it never went below, like 87,000 megawatts. And you can see the curve, and let's break this down into individuals. Let's look at the summer. So summer curve, this is in percent instead of megawatts. And so this is a very typical summer peak demand curve for any electric system. This is over a 24-hour period. So you see you start at midnight and the demand keeps coming down to this minimum down here, in this case, about 70%. What's requiring? Well, factories are open. You have factories open 24/7. Steel plants, rolling mills, whatever, large industrial customers. And so you never go below 70%. In this particular case, they're not going below 70%. And so we call this the base load on the system. This will become important when we talk about generating plants and how we use different plants to provide service during the day, how we follow this, because we have to follow that need. And then as it gets hotter during the day, air conditioning comes on, and that increases the load. So most of the summer load, the major part of that peak load is air conditioning load in the summertime. But you do see this demand valley right here. And so there's a clue right there. Charging electric vehicles during the early hours of the morning in your garage is ideal. What would really be ideal is the more you can flatten this curve out, the more efficient the operation is, because you're not starting and stopping generating plants. So you want to try to flatten that out. Yeah. So there's this demand valley in the summer. Well, there's a demand valley in the winter as well. The winter demand looks a little different than the summer demand, because in the winter demand, you have heating demand in the morning, because there is a lot of electric heat, even in PJM. There are some heat pumps, there's some resistance heat that comes on. And there's also a lighting load that comes on. And then you see another lighting load, electric lighting load, less these days from LEDs, late in the evening, or I'm sorry, in the early evening when people go home and they plug in their, they turn on their lights and everything. So the base load in the winter is still high. You have an intermediate demand, and then you have smaller peak demand areas. Those all have to be served. And we'll look at how we do that very shortly. Spring and fall are very similar. I'm just showing one chart here. It's sort of flat. There's not much of a peak demand during spring and fall. There's not a lot of air conditioning or heating load. HVAC is a huge demand on the system. That's a really, really big demand. So this would be the spring or fall peak day. But again, you've got this demand valley in the morning. Let's talk about generation now. Let me go back. Any questions about demand and what those load curves look like and why they are what they are?
Quick question.
Yeah.
So the y-axis was 100% on both of those, but what is the relative kilowatt hour summer versus winter?
Well, it's kilowatts, because we're looking, well, there is both, but we're looking at peak demand, so demand is instantaneous. And I didn't record, let me go back a second. Let me just go back a couple of them, because I think we can see it on this one. So there you can see, this is in megawatts. So this is in thousands of megawatts. So the area under these curves is the energy. That's the megawatt hours, is the area under the curve. But the actual value, the actual y-axis is megawatts. So you can see the relative difference. So PJM, definitely a summer peaking system. And much higher in the summer than it is in the winter. If you went down to Florida, you might see summer and winter or here's winter here. Summer, winter, and summer sort of vie for each other. A lot of electric heat in Florida. Very sharp peaks just during the morning.
I think if I could add,
So please.
over the entire year, right? If we look at 8760 hours, right? Speaking from my perspective, we had twice 100% more capacity to address 100 hours of that 8760. So it's even, in my opinion, it's even more dramatic of a demand management issue when you look over the totality of the year.
So you have to have that.
Everybody's paying for that infrastructure, right?
Yeah, good, excellent point. So we got to pay for it. It's got to be there.
And then just a quick follow-up.
Yeah.
Do you know how these curves have changed since the pandemic, with people staying
Oh,
at
I have no
home and
idea.
offices having different hours and all that sort of thing?
I don't know. I really don't.
It is changing, maybe a sidebar.
Yeah.
Okay, yeah, I don't want to get.
Yeah, good. Sidebar. Let's go into generators here. And I'm keeping track of the time. So then let's talk about the different kinds of generating equipment that's out there. Steam turbine generators provide most of the base load that's out there. These Essentially, you burn either coal or, and we don't burn any oil anymore, you either burn coal or natural gas. It goes into this ginormous boiler. It's a huge fireball inside. You can't even look at it. It's like the brightness of the sun. And through a lot of, there's water walls on the sides of the boiler that are picking up the heat. And then you go through you go through superheaters and reheaters, et cetera. Goes into a steam turbine. The steam comes on the top of the turbine, comes out the bottom through a condenser. And then you return the water to the boiler. This is ultra pure water because we're operating at 1,000 degrees steam temperature and about 2,500 pounds per square inch coming out of the top of the boiler. I mean, this is serious stuff. And so you condense the water and send it back. And this condenser is cooled by either a cooling tower or by river water or something like that. That doesn't mean it's a nuclear plant. Okay, a lot of nuclear plants have those. That's just a natural draft cooling tower. You have them on any kind of generator. The stack gas comes out here, it goes through filters and scrubbers, and then it goes up the stack. You normally shouldn't see any smoke coming out that stack. If you see something white coming out the stack, it's water vapor. There's a lot of, especially in coal unit, a lot of water vapor in the coal, or a lot of water in the coal. These generators run 24/7 for weeks and weeks and weeks and weeks and weeks under these extraordinary temperatures and pressures. And occasionally you may have a water tube failure, or you may have or the generator may have a problem. And then once a year or so, or maybe twice a year, you take them down for maintenance in the spring or fall. Extraordinarily reliable. This is what one looks like. I would guess, I don't know what size this is. My guess is maybe 500 megawatts. I'm not sure. There's the turbine. 2 stages, high and low pressure turbine. There's the generator, the exciter that provides the DC power to energize the rotor on the generator. So that shaft is spinning 3,600 RPM. And it just, I say, it runs forever. Efficiency of these large steam generators, about 45%. This becomes important when you start talking about electric vehicles, when people will say, well, I'm just replacing gasoline with coal. It's true. However, gasoline engines are about 20-something% efficient, and coal-fired power plants are 45% efficient. So the efficiency gain is arguably better from a coal-fired plant, but you do have losses through transmission and generation. But just so you'll have some walking around numbers, nuclear plants really work the same way, except for the fuel, we're using nuclear fuel to boil the water to turn the turbine. But usually these plants are operating at a lower temperature and a lower speed, 1,800 RPM for coal generators, and efficiencies of about 37%. Let's look at intermediate and regulating load service. And we talk about regulation because if you were really to look at, if you plugged in the oscilloscope and looked at the demand on the system, it's actually jiggling like this. I mean, because, you know, this is starting up and that's turning off, and this is starting up and this steel mill is going. And so we're following this demand constantly. And so the way you follow this demand is by regulating the output of these steam units. And there are valves on there that regulate the output of the steam generator, we're trying to keep the frequency at 60 cycles per second across the grid. All right, so everyone is participating in this regulation. The base load generators, these big coal units, you run them up to the top and run them full out all the time. The nuclear units, you run full out all the time. You don't regulate with them. But there are some smaller generating plants that you can regulate with. And so that's what you'll use. It's still efficient plants, efficient generating units. This is a gas turbine power plant. This would serve just a few hours. This is what this gentleman was talking about here, that you would run some gas turbine generators to cover the peak demand during those few hours. They start quickly and they're very inefficient, but you don't run them often. But again, the advantage is they start very fast. I mean, within a couple of minutes, you can have one of these online. Yeah, sure.
Efficiency is that the amount of heat energy that we're actually converting to electricity.
Oh, yeah.
Efficiency. Yeah.
Thank you, Chris. Yeah, the efficiency we're talking about is BTUs in to the boiler versus electric BTUs coming out of the generator. The rest of it goes up the stack and through the condenser, mainly through the condenser. And you can't do any better. I mean, the limits are the limits of, you know, of the material. So you know, we're already producing steam at 1,000 degrees Fahrenheit. And if you go too much further, you're either going to melt the tubes in the boiler or you're going to melt the turbine. And so, you know, efficiency is the heat source versus the heat. It's the delta. It's the ratio of the heat source to the heat sink. So if you can run colder water through the condenser, or you can get more you can run the steam temperature higher, you're going to improve the efficiency, but right now, 45% is about the best we can do with a coal-fired plant. Now, there is another type of generation called combined cycle, and we've seen a lot lately. You have a gas turbine in the front end, and instead of just exhausting the gas, and this is because in a gas turbine, you're losing all this heat out the back end of the gas turbine, just goes into the air. That's why the efficiency is low. You can take the exhaust, create steam and run a steam turbine on that, and then your efficiencies go up to about 65%. Well, this is very popular these days. There's a lot of gas, a lot of combined cycle generation out there, and it serves it can be base load generation. Very nice. Let's talk about renewables and their role in all this. Renewables, hydro. Hydro will decrease slowly over time. Hydro plants are wonderful. They're great for regulation service. You can start them quickly. You can regulate with them very nicely. Some might be base load, depending on whether you've got to get the water through the dam to get it down to the next dam, like on the Columbia. But the problem is that they cause environmental damage, and we're just beginning to realize some of the problems that hydro dams cause. And it hinders fish migration and, such as that. So dams are coming out. But anyway, so we're not going to see more of it, but hydros certainly has a role. Wind generation, when it's available, fine. I've looked, yes, ma'am.
Does hydro, like, do you mean by water or like hydrogen?
Water. Oh, no, not hydrogen. We're talking water. So you have water behind a dam. You have a penstock that takes the water from up here and it runs down to the bottom, and you have water wheels down here that are turning generators. So it's hydroelectric and it's water. Yes, ma'am.
And how efficient is hydro?
I don't know. I mean, it's very, but I don't know how to compare. Never thought about that before. I don't know how to compare the kinetic energy of water with the electric output. I just don't know how to do that. I haven't thought about it before. It depends. It probably depends on, I don't know what it depends on. The height of the water. I'm not sure. Interesting question. So we have wind. It's an intermediate. It's an intermittent source. It's good. I've heard wind generators are really cool and neat. But you can't necessarily rely on them. You get energy out when the wind blows. I think the biggest of these right now, I don't know, 5 to 10 megawatts for the really giant ones. So you need a whole lot of them, because I mean, consider that a single coal generating station could output 1,000 megawatts, and you're talking about maybe 10 most from one of these. So you need a lot of them to equate to the output of a coal-fired power plant. And of course, the coal-fired plant is only limited by the amount of coal in the coal pile, whereas here you're really at the whims of the wind. But they certainly have a role. Solar power, the same kind of thing. These use heliostats. This is a mirrored system that focuses the sun on these towers here. This might be 150 megawatts out in the deserts. And there are not a lot of these, but it takes up a lot of room, but wonderful when the sun is there. It's quote free, except for the capital cost of running it, or direct energy conversion in solar panels. So they have a role. They absolutely have a role. This is PJM. I took a picture yesterday of the generation from the PJM network, and you can see this is the generation for the power output. I guess this is instantaneous for as of 1 p.m. yesterday. So this is coal. This is natural gas. There's a lot of natural gas burned in our country, a lot of it, either in combined cycle or in conversion of coal generators to burn natural gas. And you can do that if you're near a gas pipeline. It's simpler. You don't need a coal pile. It's cleaner, because when you're burning coal, you're burning mostly carbon. When you're burning natural gas, you're burning carbon and hydrogen, because it's CH4. So you get a lot of energy from the hydrogen and probably half as much CO2. So natural gas is wonderful. We can have debates about whether it's a good idea to burn up fossil fuels to boil water. But anyway, there's a lot of natural gas being burned in the United States.
But the gas in this case is working on the base load?
It
Or
could be
combined,
all of it.
part of
It
the
could be
peak
base load, it could be intermediate, it could be running combined cycle, it could be all of it.
Okay.
It could be all of it. Thanks for asking that. Nuclear, there's a good bit of nuclear energy in the peak between the New Jersey nuclear plants and out in the Chicago area. So they, good nuclear energy. You can see wind was producing a respectable amount of energy there, not much from solar. I don't know what the others are. But over here, this is just the renewables. So the renewable portfolio yesterday or generation, most of it was wind, and then you can do solar, hydro, and other, whatever other is. This is from the Energy Information Agency from the US government. This is a projection of fuel used for electricity over up until the year 2025. I made this estimate for hydro. I think, from what I can tell, this is the energy solution hydro, and then the rest of this lighter blue is from renewable sources. This is coal, natural gas, and the nuclear at the top.
And this is for the US market.
That's for the US. Now, I'll take off my general, engineer hat, my personal hat. My personal hat says, I don't think so. I don't think this is going to happen. I could be wrong, but I don't think it's going to happen. For a number of reasons. And I don't know if I've got, let me see here just a second. No, I don't. But if you remember when we went back at the map, most of the wind, for example, most of the potential for wind power is over in the Midwest. And most of the load is over in the East. And there isn't enough transmission to get a lot of wind energy from the Midwest over to the East. So it becomes a transmission constraint. That's where we've got the problem in the United States, is building more transmission lines. Because nobody wants to have a transmission line in their backyard. There are states that don't want transmission lines coming in and out of their state because it doesn't help them any. It's going to go from this state all the way to the East Coast, and they don't want any part of it. So building transmission is very difficult. There are permits. Every state has its own requirements. So you can't just say, I'm going to build a transmission line, from Nebraska to New York and expect all the states in the middle just fall in line. No pun intended, but it just doesn't work that way. So one of the biggest constraints for renewable energy, in my opinion, is going to be transmission. Now there's a lot of wind energy being built off the coast, and we'll have to see how that goes. My other concern about it, and there may be ways around it, is the control. It's an intermittent source, as I mentioned. You get wind energy when the wind blows. It's hard to regulate with that. And I don't know, because energy storage is just a big problem right now. The batteries are not there for utility grade energy storage. The only other way you can really store large amounts of energy is through what's called pump storage hydro. So imagine that hydro facility that I just showed you with a big reservoir behind it, and the generators could be turned into pumps. And there are facilities that can do that. And so when you have excess generation on the grid, especially in the early hours of the morning, you can fill the reservoir up. And then later on in the day, you can let the water back down. And you lose about 30% of the energy doing that. But the economics may well be there. And so pump storage hydro is a way of storing vast amounts of energy. But other than that, battery technology is just not there yet, but it may be. I mean, that's the problem. If you can generate with wind energy, whenever the wind blows, just let them run. And if you don't need it, you store it, or same thing with solar. And right now we really can't do that, not very effectively. So I don't know what this number is going to be, but I just don't see it coming out here. The other reason, and again, I'll go into just a bit of editorializing. We do not have a national energy policy in this country. If we did have a national energy policy in this country, then it might, maybe it would say, all right, we want to be 25% renewables by then. Nuclear, which to me is underutilized and would really solve a lot of problems. We ought to be, like France is 75% nuclear. We ought to be 50% nuclear, let's say 20% renewables, and the rest filled in by gas, because you need something to regulate with. If you had a national policy that did that, then you could write your regulations, the EPA rules, the regulating rules, the monetary rules, and everything else to get you there. So you could help utilities build nuclear, help the utilities build wind and solar, but we don't have that. And so it's kind of left up to the individual states. And as you saw, the grid doesn't pay any attention to state boundaries. It just runs all over the place. And so as long as we depend on the marketplace in the states, it's gonna be very hard to get to any goal that we're trying to get to, because it's just, you don't know what you're really aiming at. I think 11:05 is our ending point, and I need to end. Are there any last minute questions before you all go to your next section?
You look like you're actually 11:10.
It's 11:10. There's
11:10, but we actually
break.
have 6 minutes left.
6 minutes left. Yeah.
I can take questions if you like, or whichever. Yes, in the back, yes.
So the way that this system is designed is, you were saying specific to the US and Canada. How would it be different, say, in Dubai?
Oh, I don't know how it works in Dubai. I know how it works in Europe. Europe has the same setup. I don't know how this works in the Middle East. I don't know whether Dubai is connected to other systems. I would think it would be, but I don't really know. I mean, I know it is in Europe for sure. I've talked to my former counterparts in Europe, and they have the same problems. I mean, same thing. Interesting question about Europe. Let me just talk about this just a minute. I wasn't going, but let's talk about geopolitics for just a minute, okay? So we look at when Germany decided about 5 years ago, they were going to shut down their nuclear units and go with wind power. And at the same time, they were buying a lot of natural gas from Russia. So they shut down the nuclear units. And they did run into they do generate a lot from wind. They did run into transmission issues. I think they had trouble building transmission down in Germany. But they were trying to become renewable plus gas. And then we had Ukraine. And then so Germany lost its gas supply. What do they do? And so what they're doing is they're burning more coal. And it's really, so underneath all of this, my only point in all of this is what underlies a lot of this when we're talking about energy or geopolitics. For example, oil is traded on a global market. The price you pay for gasoline at the pump isn't just set by Exxon or Shell here. It's a global market. With global market. Natural gas less so, but still some, because US is selling liquefied natural gas to Europe right now. So that plays a role in this as well. So, either on top of or underneath all of these energy issues we have right now, there are geopolitical issues that are involved here that do drive some of this. So there are some that argue, gee, if we just became all nuclear, we'd be totally energy independent. And I think there's a lot of merit in that. You can't get off the fossil fuels totally, because you've got to have some way to regulate output. And really, fossil fuels is a good way to do it. Gas units and things like that. So I think what's frustrating to me, and maybe it's up to you all, but when you read news articles about the electric system or energy, there's so much more than what you're just reading. It's so much deeper. And that's one of the reasons why I really appreciate the opportunity to come here and talk to the history. Because when you start talking about electric vehicles, you're going to hear, they're wonderful because of this, and they do this and that and this and that. And I think that all of us need to have for this basic understanding of how all this works. So you'll know, yeah, you can plug them in the morning, and we do know where the fuels are coming from. But then underlying all this other stuff, we have all the stuff going on in the world. And so those are all things, it's all part of the big picture. So it's not really too simple, but it is interesting. Yes, sir.
I guess it was a few years ago that there was this event that was triggered by like a squirrel in Rochester or something like that. And there was this whole cascade of events that it triggered. And everyone was saying, our infrastructure is, totally.
Oh, yeah.
But
Right.
what has happened since then to avoid that sort of cascading effect?
What's happened is that the reliability rules that NERC wrote became federal laws. And so that event was not a squirrel, I don't think. It was 2003, and it was in Ohio, and the transmission line overheated and sagged into a tree. Utilities are supposed to keep their rights of way trimmed. And if you look at right of ways where the big lines run, you will see no trees. I mean, it's just cut right up. It's just like a hallway, right? That's what you're supposed to do. They had a transmission line sag into a tree. That transmission line is protected by circuit breakers that remove the line from service. And so the power climbed onto the other lines, and it caused those lines to sag into those trees because they were not doing their vegetation management. And from there, through this incredible sequence of events, it blacked out the Northeast. It was the most embarrassing thing I've ever been through in my life. I ended up writing part of the report for that. It was awful. We had news trucks in our parking lot the next day. But that's essentially what happened. So what they've done since then is we now have rules in place. And if you have a food contact, you could get fined up to $1 million. I mean, the electric company can. So we put in rules. And the electric systems also now formed a peer organization where they review each other's operations and they beat up on each other if they're not doing things right. And that helps a lot. By the way, the nuclear industry has had that for the last 40 years. It's called the Institute of Nuclear Power Operators. And that's why nuclear units here in the US run so well, because they beat up on each other. The CEOs of the companies are involved in it. They are really serious about making sure the nuclear units run very, very well. So that was after 3 Mile Island. So eventually you have a catastrophe and then the industry comes together and says, oh my God, we better fix it or the government's going to fix it. And we don't want the government fixing anything if they fix it. Anyway. Everyone have a wonderful